Hey everyone, so here we are again. My name is Crystal Abbey. I'm your instructor this semester, and today we are going to cover Chapter 2, which is the chemical basis of life. Okay, and so again, I'm going to be trying to use my little Wacom device to draw on my PowerPoint as best as I can. So please do bear with me as I continue to try to learn how to use this little contraption. So 2.1 of our text starts with the basics on atoms and atomic bonds. So if we recall from last chapter, Chapter 1, we defined, we talked about what an atom is. Atoms are the smallest functional units of matter. And remember, matter is anything that takes up space. Doesn't matter if it's a solid, liquid, or gas, it's anything that takes up space. Living things, non-living things, as long as it's taking up space, it's composed of matter, and matter is made up of atoms. So the desk that I'm sitting at, non-living, it's still made up of atoms. Me, I'm a living thing. I'm taking up space, therefore I have matter, and I am made up of atoms. Now the difference between the atoms of myself and the atoms of my desk as a non-living thing is that the atoms of myself are going to be organized into molecules, which will then organize themselves into cells. My desk has atoms that will be arranged into molecules, but then they don't arrange themselves into cells. So there's the difference, again, between living and non-living things when it comes to organization. Don't forget those things. Definition of a unit or of a cell, atom, they are different. All right, so again, cells, basic unit of living things. Atoms are the basic units of matter, both living and non-living. Okay, so atoms can be bound together with other atoms. They can be bound to other atoms of the same type or of a different type. If they are bound to the atoms of the same type, we call that an element. So here on the left, we see a little green ball. This is representing a single atom of carbon. Here, we have two atoms of hydrogen. That's H. Because we have two atoms that are of the same type, that is an element. All right, this is an element. This is an atom. So there's our difference. We could also have O2. O2 is two oxygen atoms. H2 is our two hydrogen atoms. That. O2 would also be an element. That's what an element is. It's just two atoms of the same type that are bound together. Now, in living things, 95% of an organism's mass, 95% of our mass, humans, a toad, a fish, any living thing, is made out of only 4 different atoms or elements. And those elements I'm going to represent as CHON. CHON, okay? C-H-O-N. And that's another anagram, or is it an anagram? I always get these mixed up. What's it called? Acronym. An acronym that will represent those elements. C stands for carbon. H stands for hydrogen. O stands for nitrogen, or excuse me, O stands for oxygen, and N stands for nitrogen. Okay, so again, C stands for carbon. Carbon is the main building block of pretty much all organic molecules. It's one of the requirements to call a molecule organic is to contain carbon as well as hydrogen. But 95% of an organism's mass is going to be CHON. And the C, which stands for carbon, is mainly tied up in building blocks of organic molecules that are found in our body. Oxygen and hydrogen is primarily found in water in the body. Most of our body is actually made up of water. And then lastly, the N stands for nitrogen. So nitrogen is largely found in proteins. Our body has hundreds of thousands of different types of proteins that makes our body function properly. So if you look at this image over here, this shows you a pie chart of some of the various elements that are found within our bodies and their respective percentages. So you can see oxygen here, we're 65% oxygen. Again, most of that's in water. We're 18% carbon. And we are 10% hydrogen. Again, most of that's going to be in water, because what is water but H2O? It's two hydrogen atoms and an oxygen atom bound together. All right, and the rest of it, we see 3% of us is nitrogen, calcium, phosphorus, and then other smaller things, lesser elements like sulfur, trace elements, 0.6%. All right, but overall, grand scheme of things, what I want you to know here is 95% of a living organism's mass is CHON, C-H-O-N, carbon, hydrogen, oxygen, and nitrogen. Now, the components of living things are very, very different when we compare them to non-living matter. And this chart represents that here. So if we look at this chart, we're going to see various elements that are listed at the bottom. This is a bar graph, by the way. And then their percent by weight is going to be up here on our y-axis. And then in blue, it will represent the different components and their percentages of the Earth's crust. And then in red, we have of living organisms. So if you look over here to the right in red, we see mostly we are oxygen, same thing that our previous image said. We also are composed of a lot of carbon and hydrogen and nitrogen. What do you know? That's CHON, C-H-O-N, carbon, hydrogen, oxygen, and nitrogen. Now, of course, we have some other things we are also composed of. We said calcium, sulfur, for example. Some other smaller numbers are here. A little bit of sodium and magnesium, phosphorus, potassium, iron. All right, but they're just in much smaller quantities. 95% of our mass is CHON in living things. However, in non-living materials, it's very different. They don't have nitrogen really, or carbon, or much hydrogen. They're mostly oxygen and silicon, aluminum. And then we see a good bit of iron, magnesium, sodium, calcium, potassium. So overall, these are the components that are primarily made up in non-living things, and these are the ones of living things, and they are very different from one another. All right, so here's some examples of those mineral elements and trace elements that we mentioned in that picture with the soccer ball player. Mineral elements are elements that are less than 1% of the total mass of the organism. So remember, 95% is CHON. So that other 5% is mineral elements and trace elements. Mineral elements is less than 1% of the total mass. And then trace elements are elements that are less than 0.01% of the total mass. So trace elements means, there's just a very tiny amount in our bodies. So the mineral elements include things like calcium and chlorine and magnesium, phosphorus, potassium, sodium, and sulfur. Trace elements include things like boron and fluorine and iodine and iron and magnesium, tin, and zinc. You don't need to remember all those, by the way. You do want to know CHON. You need to know that living things and non-living things are very different from one another when it comes to what they're made up of, but I do not expect you to memorize these charts here. Okay, so you don't have to do that. However, some things you should know are that even though those trace elements are found in very small quantities in your body, that doesn't mean that they're not important. And if you don't have them, even though that they're in small quantities as it is, if you don't have them at all, that can be deadly. So, for example, iron was an example of a trace element that is found in our bodies. Iron is an atom that is a component of a protein called hemoglobin. If you've ever had blood drawn, you might have even talked to your doctor about your hemoglobin levels and stuff. But hemoglobin is a molecule that is packed within red blood cells. And in those red blood cells, that hemoglobin works to help transport oxygen. So when we breathe in our lungs, Breathe in. We just breathed in oxygen. That oxygen that's in the lungs is going to be transported to the red blood cells. Because at the microscopic level, your lungs are infiltrated with, there's the alveoli, little sacs that make up the lungs, are surrounded by capillaries, which are little tiny blood vessels. And so the oxygen that's in your lungs is moved to those blood vessels and then into the red cells, which is then packed and loaded up on hemoglobin molecules. So that way we can transport oxygen in your bloodstream into other tissues, like your brain. If you don't have oxygen in your brain, well, that's going to cause brain damage and then eventually death. So anyway, that iron is required for that oxygen to be loaded properly onto the hemoglobin. And so in the absence of iron, that results in anemia. Anemia is a decrease in the oxygen carrying capacity of your blood. The most common type of anemia is iron deficiency anemia. So people that have iron deficiency anemia usually have to take supplements of iron, while most of us usually get it through our diet. Second most common type of anemia, B12 deficiency, because B12 helps iron that we ingest move from the gut to the blood. So if we can't get the iron in the bloodstream due to B12 deficiency, then of course it results in anemia. All right. Next, goiter. Goiter is the results of hyperthyroidism. Break it down. Hyperthyroid. That means that you have an overactive thyroid. Your thyroid is a gland in the neck that looks kind of like a butterfly. And whenever it's overworking, can result in goiter. Goiter is this large enlargement of the neck area here. And this goiter can be caused by iodine deficiencies. So because this person has not enough iodine, it causes the thyroid to overact and therefore become enlarged. All right, so in this case, iodine, that was our trace element. All right, tooth decay. So fluoride, that's another trace element found in our body. And it's actually added to toothpaste and water even to help strengthen the enamel of our teeth. And without it, it would cause tooth decay. So again, just because these trace elements are found in very small concentrations does not mean that they're not critical for life. Okay, so now that we've discussed a little bit about what atoms are and what elements are and how they relate to the human body or living things in general, let's talk about the nitty-gritty of what in the world an atom is. And to start, we're going to talk about atomic structure. All right, so let's talk about their structure. Structure means how they're built. The atomic theory states that elements are going to consist of atoms, and those atoms are going to be consisted of 3 subatomic particles. What in the world is a subatomic particle? Again, break it down. Subatom. Sub means under, and atom here will mean atom. Okay, so what's under an atom? Think about like when I say under an atom, meaning like the next level underneath it, meaning something smaller than an atom. That's exactly what that means. Subatomic particles are kind of like Legos. They're little Legos that are going to build the atom. They're the pieces that make it up. And those pieces are 3 things. There's 3 particles: protons, neutrons, and electrons. The protons and the neutrons are located in the nucleus, the central nucleus, in the center. And then surrounding the nucleus, we have electrons that orbit around the nucleus in what we call electron shells, or the electron cloud. Some texts may say that instead. So here's a great rendition of that here at the bottom. We have our protons in here in that yellowy, or I guess it's orange color. We have our neutrons in the greeny color. And then we have our electrons in the blue. And you'll notice when I write electrons, I'll write E with a little negative sign. That's the chemist's shorthand, if you will. So protons and neutrons in the nucleus, electrons in the electron shell surrounding it. All right, so some additional things you need to know about these subatomic particles are their mass and their charge. So we talked about their location already. Protons and neutrons in the nucleus. The electron shell houses the electrons on the outside. You need to also know their charge and their mass. Protons are positively charged. My son's baby shark toy just went off. Sorry. Where is it? Okay, I found it. All right. Sorry about that. So protons have a positive charge. Neutrons do not have a charge. They are neutral. No charge. No charge. Electrons have a negative charge. So protons, positive. Neutrons, no charge. They are neutral. And electrons have a negative charge. Next, the atomic mass. Protons and neutrons have an atomic mass of 1 atomic mass unit each. And then electrons are so tiny. They're itty bitty bitty bitty. They're so little that their mass is negligible in calculation. So we basically just say that their mass is 0. All right, so again, protons and neutrons are located in the nucleus. The electrons are in the electron shells. Protons are what charge? Positive. Neutrons are neutral. Electrons are negative. Protons and neutrons have an AMU, or a mass of 1 apiece. And then electrons are going to have a mass of 0. Okay, so you need to know all of that. I put it into this nice little chart here and made it available for you because I like charts, and I know a lot of y'all probably are similar and like to remember things based on looking at pictures. Okay, here's another example of a model of a atom. This one is helium. So if we look at the protons, they are going to be in red, neutrons are purple, electrons are in blue. So this is our traditional Bohr model, which I just showed you in a previous picture, the one on the previous slide. So you see we have our 2 neutrons, we have 2 protons, and we have 2 electrons. Now I could also draw it like this. This is showing you the electrons in the electron shell format. That's the typical of a Bohr model, B-O-H-R, if you're curious how to spell that. And then this is a different type of model, less commonly used. So pretty much you're always going to see me use this type of model. Okay, so that's the general information on the subatomic particles of an atom. They have protons, they have neutrons, and they have electrons. Now, what information can be found on our periodic table? So this is probably something you've seen before in, high school, maybe even middle school. But it's our periodic table of elements. This shows you all of the elements that are known to man at this point in time. Some of them are naturally occurring, well, most of them are naturally occurring, and some of them are man-made. So for example, I believe, and I will admit that I'm not a chemist, but I believe these are the ones down here that are man-made, whereas the ones up here are naturally occurring. But don't quote me on it. I won't ask you that on an exam. Again, I am not a chemist. I'm a biologist, but I'm going to do the best I can. Okay, I know the general concepts of chemistry. So what information can be found on this table? That's going to be very important. So each one of these squares represents a different element. And each square is going to have an array of information on it. So I actually took this, which shows you pretty much what's found on each square, and blew it up really big so you could see it better. But each one of these squares that represents a different element is going to have the atomic number We'll talk about what these are in a second. At the top left-hand corner, it's going to have atomic symbol. It will have the atomic name, the atomic mass, and this particular atomic or periodic table also includes the boiling point. Now, if you just Google a periodic table, some of them won't have all of this information. Some of them might just include the number and the symbol. Some of them might include a lot more information. Like I have one in my classroom that will even go as far as to explain the electron configurations of each one. But this one doesn't do that. It just shows you the items here. And these are the ones we're going to want to know about. We won't talk about boiling points really, but these things. Okay, so let's start with atomic symbol. The atomic symbol is just what it sounds like. It's just a symbol that abbreviates the name of an atom. So for example, hydrogen is H. Lithium is Li. Beryllium is Be. Magnesium is Mg, and sodium is Na. All right, and so that's just a few examples. Next, the atomic number. The atomic number is equal to the number of protons in each atom of an element. The atomic number, that's the number of protons in each atom of an element, and it's going to be found in our top left-hand corner. So if I were to ask you how many protons hydrogen has, you would tell me 1. If I were to ask you how many how many protons beryllium has, you would tell me 4. Okay. This is the number that's going to determine what kind of atom you have. So if I find an atom and I run tests on it to see what kind of atom it is, and I find that it has 12 protons, then I know that that atom must be magnesium, because all magnesium atoms have 12 protons. All carbon atoms have 6 protons. Go back and look at your periodic table. Now, the periodic table is organized by atomic number in increasing order from left to right, just like you're reading a book. Excuse me. And I'm going to go back and show you that. I know this is in the way here, but if you look in your textbook, there will be a picture of a periodic table, or you can just Google one. But you'll see 1 is here, hydrogen. 2 is here, helium. I know you can't see it. 3, and then 4. Then 5 and 6. And then there would be 7, 8, 9, and 10. Then we have 11 and 12. We have 13, 14, 15, 16, 17, 18. 19, 20, 21, 22, 23, 24, and so on and so forth. So it reads just like a book in increasing order. So this atom, hydrogen, atomic number 1, has 1 proton. Helium, which I know you can't see, has 2 protons. Lithium, 3. Beryllium, 4, and so on and so forth. All right, so if you were to find an atom and determine it has 11 protons, what atom have you found? You can look right over here because it's in this little excerpt of the periodic table. And if you guess sodium, then you are correct. Now, another thing to know or to note about our periodic table is that the atoms that it lists are on there. The atoms that it lists on the periodic table are all electrically neutral. And so what that means is that they don't have a charge. So if hydrogen has 1 proton and it is electrically neutral, how many electrons will it have? I'll ask again. If I have a hydrogen atom and it is the atomic number is 1, which means it has 1 proton. We said it's electrically neutral, so how many electrons does it have? If you said 1, then you're correct. Because in order to be electrically neutral, we had to have just as many positive charges as we do negative charges to cancel each other out. So, all in all then, if this hydrogen has 1 proton and is electrically neutral, then it must have 1 negative electron, or it must have 1 electron. Okay. Okay, so that was atomic number. Next, we're going to look at mass number and atomic mass. So the atomic mass is the weighted average of all of an element's isotopes. And we'll get to what isotopes means in just a minute. But that number is going to be located here at the bottom. So the atomic mass of hydrogen is 1.008. The atomic mass of beryllium is 9.012, etc. And again, those numbers represent the weighted average of all of the element's isotopes. The mass number of an atom is equal to the sum of the number of protons and neutrons in the atom's nucleus. So I wrote out a little equation. I like equations. Mass number is equal to protons plus neutrons. Now, the mass number and the atomic mass are almost equal for most of our biologically relevant molecules. So it's just easy to round whenever you're trying to find neutron numbers or proton numbers if you're given the mass number for problems. And we'll do some examples. But for example, we're going to do an example. If I were to ask you, what is the atomic mass of lithium? You would tell me 6.941. If I were to ask you how many protons it has, what would you tell me? You'd tell me 3 because that's its atomic number. Now I'm going to ask you, how many neutrons does it have? Well, in order to know that, you would need to take the mass number and set it equal to the number of protons and then solve for n. For the mass number, instead of putting 6.941, you'll just put 7. All you have to do is round. Because again, the atomic mass and the mass number are pretty much equal as long as you're rounding for the biologically significant molecules that we'll discuss. So you would put in 7 for the mass number and set it equal to the proton number, which is 3, and solve for n. So again, mass number 7 is equal to the proton number, which is 3, plus n. And n would then equal what? 7 minus 3, which is 4. So you would have 4 neutrons. Let's do another problem. So if I were to ask you for the number of neutrons in sodium, how would you set that up? You would first round the atomic mass, which is 22.99. If you round it, then that is 23. 23 is equal to the number of protons plus the number of neutrons. The number of protons is 11. So we set it equal to 11 plus n, which is the number of neutrons. All right, so if you were to do the math, n would be equal to 23 minus 11. Okay, so if you'd like to have any more examples of that, just let me know, and I will do my best to help provide those for you. Just contact me on Remind. But again, you do the math and you would get 12. Neutron number, or the number of neutrons is equal to 12. Okay. Now, so we mentioned isotopes. Now, what is an isotope? An isotope are 2 atoms that are the same element and they just differ in the number of neutrons. Now, neutrons can differ. Neutron numbers can differ from carbon atom 1 versus carbon atom 2. It can't differ in proton number though, right? Because we talked about how proton number defines what atom you have. All carbon atoms all have 6 protons, but they can have different neutron numbers. So a lot of times the way we will write isotopes are like this: carbon dash whatever the atomic mass is, or mass number. So 12, like carbon 12 or carbon dash 14. So that tells us carbon 12 has 6 protons and 6 neutrons, because carbon always has 6 protons. And then after we subtract 12 minus 6 to get the number of neutrons, there's 6 left. So carbon 12 has 6 protons and 6 neutrons. Carbon 14, mass number is 14. Remember, we set that equal to protons plus neutrons. 14 is equal to protons, which we know is 6 plus N. If we do the math, N equals 8. So it has 8 neutrons and 6 protons. Now, some of these isotopes are pretty neat because they can help us solve biologically relevant problems. So, for example, carbon-14 is very unstable. It decays, and therefore it can be used to estimate the age of fossils. We call this carbon dating. And so here in this picture, you can see some paleontologists working to uncover bones that they can then use carbon dating to estimate the age. Some other relevant ways we can use isotopes are in scanning patients for cancer. It can be used as a tracer dye. So cancer cells, they grow faster than normal cells do. And they also incorporate radioisotopes faster than healthy cells. So if we administer to a patient radioisotopes such as iodine-123, iodine and 123 would be the mass number, then we scan them, then we will be able to see where the radioisotopes are being taken up the quickest. And so just from scientists doing this type of scan, we know already that here and in the bladder, they kind of tend to take up, those glands kind of tend to take up these radioisotopes quicker under normal circumstances. So that's not a reason for concern. But let's look at the difference between our normal patient and our cancerous patient up here. This is our thyroid gland, and it is much darker. Ooh, I shouldn't have scribbled that. I don't know how to erase it. Let's see if I can figure it out. I have no clue. Oh, well, y'all see what I mean. The thyroid gland here is much darker than it is over here, and that's indicative or gives supporting evidence that this patient might have thyroid cancer. So some other ways that we also have incorporated isotopes are even in sanitizing your food. Okay. Some additional characteristics that we should know about in the periodic table of elements is that atoms of an element are arranged horizontally and vertically. The horizontal arrangements are called periods, and the vertical columns are called groups. So you need to know that. Horizontal rows are called periods, vertical columns are called groups. And additionally, you need to know this. This is super important. All right, atoms within the same group share the same chemical binding characteristics. And what you're going to notice later is it's because they all have the same number of valence electrons. We'll talk about that. All right. And again, we've already mentioned this. The atoms on the periodic table are electrically neutral. And that means you must have the same number of positive charges as you do negative. Okay, so, and then therefore, that also tells us then that the atomic number that tells you the number of protons also tells us the number of electrons in the periodic table because it's electrically neutral and because for every positive proton, you have to have a negative electron. Okay, so let's do a couple of questions just to make sure we're understanding. How many periods are shown here? This is a small excerpt of the periodic table. All right, you should have answered 4 because periods are the horizontal rows. 1, 2, 3, 4. How many groups? All right, you should have answered 8 because we have group 1, group 2, group 3, group 4, group 5, 6, 7, and 8. Next, does hydrogen and helium have similar bonding characteristics? Here's hydrogen, here's helium. All right, you should have answered no, because they are in the same row, the same period. They are not in the same group. Remember, things that are in the same group have the similar binding characteristics. So, for example, argon and neon. Argon, neon. They would have similar binding characteristics because they are in the same group. Okay, so let's revisit the structure of an atom before we move forward, just to keep our memory jogged of how these things look. We have a nucleus inside of the center of the atom that houses our protons and neutrons. Okay. Protons are in red, neutrons are in green here. Then we have electrons that are located in the electron cloud. Okay. And these electrons are going to stay in this cloud that surrounds the nucleus because they are attracted to the protons within the nucleus, which makes sense, right? Because our protons are positively charged, our electrons are negatively charged, and positives and negatives are going to attract each other. Different charges, positives and negatives, attract one another, whereas negative charges will repel other negative charges, and likewise positive charges will repel other positive charges. Like charges repel, different charges attract. All right, so energy is required to keep those electrons in the electron cloud. So even though we visualize them in what we call a Bohr model as being stationary, that's actually not truly the case. These these electrons are orbiting and they're moving and surrounding the nucleus here. The picture that we're seeing, this Bohr model, is just it shows the locations where the electrons are most likely going to be at any given time. All right, so even though they're moving, this is where they're just most likely to be. So because of that, it's useful to construct models of atoms with energy levels or electron shells, and that's what our Bohr model is. So it gives us a rendition of what our atom most likely looks like at any given time because those electrons, again, they're moving. Now, Bohr models always put electrons in energy shells. Back up for a second. This one shows two energy shells. They're represented by the rings that surround it. 1 and 2. The first energy shell can hold up to 2 electrons. Back up. That first energy shell can only hold up to 2. Each additional shell can hold up to 8. Another rule of Bohr models is that each lower shell, the one that's more central, is filled before electrons are going to be placed in the next shell. And these rules will cover most of the biologically significant elements up to atomic number 20, which is calcium. Now, another thing you should know about are valence electrons. Valence electrons are just the electrons that are on the outermost shell. We call that the valence shell. So here you see our carbon atom. You'll notice it has 2 electrons in the innermost ring, and then it has 4 in the outermost ring. That's the valence shell. These are the valence electrons. And this valence shell is very important because these electrons that are in it are going to determine that atom's chemical reactivity. And you'll see why in just a few minutes. Another rule you need to be aware of is the octet rule. All right, let's break down octet. Oct, what does oct mean? It means 8, right? The octet rule states that the outermost shell is most stable when it has 8 electrons, which is the most that it can have, with the exception, if you have a very small atom like hydrogen and helium, they only have 1 and 2 electrons respectively. Hydrogen, when it is electrically neutral, has 1 electron. Helium has 2. So they only have 1 shell. All right, so they're happy and most stable whenever they have 2 electrons in their valence shell. Everything after that, up to atomic number 20, will need 8. That's the octet rule. Now, when our octet rule is not met, our atoms are chemically reactive. They're going to want to bind with other atoms in order to get the octet rule satisfied. All right, so again, when we do not have our octet rule met, our atoms will bind to other atoms in order to get their octet rule satisfied, to fill their valence shells with electrons to become chemically stable. So let's look at these atoms here. I want you to tell me which ones are chemically stable and which ones are not. So let's look at our first one, hydrogen. Is it chemically stable or is it reactive? It is reactive. Why? Because it only has a single electron. How will it get happy and be stable? It would need to have another electron. In order to do that, what will it do? How can it gain that stability? How can it gain that electron? It will have to form a chemical bond with something else. Here's our next one. Here we have carbon. It has 1, 2, 3, 4 valence electrons. Is it reactive or stable? Reactive. Because how many does it want to have? 8. Nitrogen, it has 1, 2, 3, 4, 5. I'm going to put valence electrons. Is it reactive or stable? Reactive, because it wants to have 8. Again, oxygen, we have 1, 2, 3, 4, 5, 6 valence electrons. Is it reactive or stable? It is reactive because it wants 8. So y'all see where I'm going with this, right? Now, we see a much larger atom, phosphorus. It has 3 electron shells. The outermost one is the valence shell. So it has 1, 2, 3, 4, 5 valence electrons. So is it reactive or stable? Reactive. And sulfur, 1, 2, 3, 4, 5, 6 valence electrons, and it is reactive. So none of these atoms that we have here are chemically stable. So in order for them to gain stability, they are going to create molecular bonds with other atoms in order to get their octet rule met. Now, before we move on, I just wanted to show y'all a couple of different models of molecules. All of these are models of methane, but sometimes our textbook will show us different types of models. So what we've been looking at so far are our Bohr models that show all the electrons and everything, which is this one right here. So you see we have our carbon atom. There's 4 hydrogens that surround it. That creates our that are bonded to it. Now, sometimes chemists will also use structural models. They're a lot more simple, like this. Ooh. It shows the same thing. It's a carbon with 4 hydrogens attached to it, just like this guy over here. It's just showing you basic structures rather than all of the different electrons. Another methodology that chemists use to model molecules are ball and stick models, and you can probably tell why they're called ball and stick, because it literally looks like a bunch of balls and sticks, but it shows you all of the different atoms of an element using balls, and then the sticks show the bond. So again, this is still methane. We have carbon and it's attached to 4 hydrogens. These are useful because they're then able to determine the degrees between the atoms that make up the molecule. And then lastly, we have a space filling model. So it just is exactly what it sounds like. It shows you for every single atom how much space it fills up within the molecule. So here in black we have carbon, and then we have our 4 hydrogens. And this again instead shows you space filling. This is the one that I will most use for our class, and maybe a little bit of this. All right, so anyway, back to chemical bonding. So we said if an atom does not have its octet rule met, it will form chemical bonds with other atoms in order to get its octet rule met. So before we discuss how all that happens, we need to know some definitions first. The first definition is a molecule. Now, previously, we talked about atoms. We talked about elements. And the elements are atoms of the same type that are bound together, like O2. It would be an oxygen atom that is bound to a second oxygen atom. Now, another definition we should be familiar with is a molecule. That's groups of atoms that are bonded together. All right, so regardless if we have O2, like over here, or if we have H2 or N2 or H2O, which is water, or this molecule here, which is C6H12O6, which is glucose, those are all examples of molecules because they're groups of atoms, two or more atoms that are bound together. Remember, elements are atoms of the same type that are bound together. So like H2, N2, O2, those are elements because they're bound to the same type of atom. Molecule is a little bit more encompassing. It includes things like H2O. They don't have to be of the same type, or glucose. Compounds are molecules containing atoms of more than one element. All right, so for example, and it has to be different ones. So again, it gets a little bit more specific. Some of these terms are kind of, they're overlapping. All right, so like element, it has to be two of the same type. Molecule is where it can be two of the same type or not two of the same type. It just has to be two. And then compound is where we have atoms that have more than one element involved, meaning multiple types, like water or glucose. Wouldn't include O2 because O2 is of the same type. These have to have more than one element. Okay, so next, chemical formulas. They tell the number in each kind of atom in a molecule. So sticking with glucose, glucose is C6H12O6. That means that there is, in every single molecule of glucose, there is 6 carbon atoms, there is 12 hydrogen atoms, and 6 oxygen atoms. All right, so here's some examples of some common molecules that you're probably familiar with in their formulas. So baking soda, most of y'all probably have that in your pantry or in your refrigerator. The fancy name for that, the chemical name, is sodium hydrogen carbonate or sodium bicarbonate, which is what most people would call it in the science community. But that's NaHCO3. So that means that it is made up of one sodium atom, a hydrogen atom, a carbon atom, and 3 oxygen atoms. Next, good old bleach, sodium hypochlorite, is made up of sodium, chlorine, and oxygen, one apiece. Cream of tartar, I have it in my pantry. People use it to cook. It's made up of potassium, a hydrogen, 4 carbons, 4 more hydrogens, and 6 oxygens. Water, which is actually the fancy name for it, is dihydrogen oxide, H2O, and so on. Okay, so we said in order to gain stability, atoms that do not have their valence shell full want their valence shell full. They want to meet their octet rule. In order to do that, they will perform chemical bonding. To do that, they will either share electrons with other atoms, or they will donate and accept electrons. So in some way, shape, or form, they are going to exchange electrons in order to meet that octet rule. And the types of bonding are as follows: ionic, covalent, and hydrogen. In ionic bonding occurs between ions. And ions, by definition, is an atom that has lost or gained an electron. And if they lost or gained an electron, then that means that they are no longer electrically neutral, right? So if we have a hydrogen atom, it has a proton. I guess I'll write P like that. And it has an electron, right? Because it's the number 1 on our periodic table. We've got 1 proton, 1 electron. If we gain an electron, then we have 2 negative charges and 1 positive charge. And so they're no longer equal, right? So that's what an ion is. It's a charged atom. So most commonly what you'll see is hydrogen will lose an electron. Bloop. So if hydrogen loses that electron, we'll now denote it as H+, because it's a positively charged hydrogen atom. Because if it lost a negative charge, it becomes more positive. There's 1 more proton than electrons. All right, so more specifically, ions that have a positive charge, we call those cations. Negative ions, which have gained an electron, are called anions. You need to know those definitions. And when we have a positively charged ion and a negatively charged ion, they're going to be attracted to one another. And that's what we call an ionic bond. All right? A great example is sodium chloride, which is table salt. Literally the stuff you pour on your food. Let's look at that example. So here we have sodium atom. Here we have a chloride atom, or chlorine atom, excuse me. So if we look at the structure of sodium, let's look at its valence shell, the one on the outside. Is it happy? No. The octet rule is not met. Why? Because it only has 1 valence electron. So let's look at chlorine. Is it happy? Is it stable or is it reactive? 1, 2, 3, 4, 5, 6, 7 valence electrons. So it is reactive. It's going to react somewhere. I'll write that here too. They're both reactive. Now what's going to happen is that sodium, since it only has 1 valence electron, is going to donate it to chlorine. And chlorine is going to accept it. That's what happens in ionic bonding. Donation and acceptance of electrons. All right, the next picture shows that, so I'll skip forward. So this valence electron, bloop, moves right over here to the chlorine atom. Now, how many valence electrons does our sodium atom have now that it donated that electron? 1, 2, 3, 4, 5, 6, 7, 8. Yay, it has its octet rule met. What about chlorine? 1, 2, 3, 4, 5, 6, 7, 8. Yay, it's happy now. It is no longer reactive. It is stable because it has both of these atoms have 8 electrons. Octet rule met. Octet rule met. Now, what about this stuff up here? We see this little positive sign, and we see this little negative sign. Well, when sodium donated a negative charge, it became more positive. Because it has now more positive charges than it does negative charges. Chlorine, when it accepted that electron, it was previously electrically neutral. All right, so before this sharing of donation or acceptance of electrons, chlorine had the same number of electrons as it did protons, meaning it's neutral. Once it accepted this electron from sodium, now it has 1 more negative charge, 1 more electron than it does protons or positive charges, so it became more negative. And we said ionic bonding occurs due to the attraction of ions, which are positive and negatively charged molecules. So this positively charged sodium is now attracted to this negatively charged chlorine, and that is what the ionic bond is. They're attracted to one another, and that's what table salt is. All right, if you look at it in a microscope, it crystallizes like that. And this is what it looks like when you have lots of sodium and chloride together. So all the little green balls are chlorine, and then all of the little orange balls are the sodium. All right, so here's some examples of some common ions that are found in the human body. You do not need to memorize this table, but I just want to show you some examples. So some positively charged cations are here: sodium, potassium, calcium. Anions, chloride, bicarb, sulfate. So just to make sure we're understanding, if we have this one here, calcium 2+, calcium 2+. How many electrons were gained or lost to get calcium 2+? So remember, we're starting off with an electrically neutral atom. In order to get to 2+, which is more positively charged, we would have to lose 2 negative charges. We can't gain 2 positive charges, right? Why? If we gain 2 protons, then we don't have calcium anymore. Remember, our atomic element is determined by how many protons it has. All hydrogen has 1 proton. All carbon atoms have 6 protons, and so on. So calcium, you can't gain and lose protons and it be the same element. So we had to lose 2 negative electrons in order to get calcium 2+. Okay, the next type of bond is covalent bonding. So in ionic bonding, it occurred between ions that lost and gained electrons. They donated and accepted. Here we have covalent bonds that share. All right, you need to know that difference. They share valence electrons so that they meet the octet rule. So here's a great example here. We have 2 hydrogen atoms. Remember, hydrogen by itself is a proton and an electron. So if we have this hydrogen atom, is it happy? No, because it only has 1 valence electron. How many does it want to have? Some of y'all just said 8, but the answer is 2. Remember, these 2 small atoms, hydrogen and helium, they're happy when they have 2. That's our exception to the octet rule. So if we have, here's our second hydrogen atom. There's 1 proton. Here's my other electron. Instead of donating and accepting, they're going to share these 2 electrons amongst each other. All right, and that's what this picture shows. Hydrogen atom 1, hydrogen atom 2, and they are sharing their electrons between each other. So that way now they both have 2 electrons, and that means it's happy. It has met its octet rule. Now, sometimes you might see the book write H2 like this, H-H. It says the same thing. That's a structural formula, just like I showed y'all with methane. Just to remind y'all of that line right here. If I were to draw hydrogen gas using a structural formula, this line indicates 1 pair of shared electrons. The molecular formula like this, all it shows is you have 2 hydrogen atoms. But in a chemist's mind, they already know that that means that there's 1 pair of electrons shared between each other. Okay, however, sometimes we have something called double covalent bonds. So what we just saw was single covalent bonds. Sometimes things can have double bonds. This is where 2 atoms share 4 electrons instead of 2. All right, so backing up, we had 2 atoms sharing a single pair of electrons. Now we're going to have 2 atoms that share 2 pairs, or a total of 4 electrons. So you see there's 4 shared here in oxygen. So if we write the structural formula of oxygen, I'm going to write it over here, we would actually write it like this: a double bond between these 2 oxygen atoms. This represents a total of 2 pairs of electrons shared between the 2 of them, a total of 4 electrons. All right, so again, for the molecular formula, we just write O2. This is the structural formula demonstrating that there's there's a double bond between them. All right. Okay. So like we already said, covalent bonds result when atoms share valence electrons. We talked about single bonds. We talked about double bonds. Now, something we have not spoken about is the difference between nonpolar and polar covalent bonds. Okay, we'll start with nonpolar covalent bonds because it's easier. Nonpolar covalent bonds share electrons equally. All right, that's big, equally between the atoms. So here's some examples here. You can see that in hydrogen gas, we have these electrons and they're right in the center. They're sharing them equally. Our carbon atom is sharing the electrons with each hydrogen atom equally. Now, in polar covalent bonds, however, our electrons are not shared equally. They are shared unequally. And a way to remember this, polar, when you have something that's polar, it has poles. It has ends, like the North Pole and the South Pole. They're different ends of the Earth. In a covalent polar bond, it's going to create poles of the molecule. And at each pole, it's going to have a charge. All right, so in a polar covalent bond, electrons will spend the most time around the atom with the most protons in its nucleus. And I know you're probably kind of overwhelmed right now. It's okay. Deep breaths, deep breaths. Let's think about why. Here is an electron model of the molecule water. All right, so here in blue, this is representing the oxygen and its electron shells. And here we have hydrogen and hydrogen. Remember, water is H2O. So we have an oxygen and 2 hydrogens. Now, which one has more protons? Oxygen or hydrogen? Look at your periodic table. Hydrogen is atomic number 1. It's the very first atom. That tells us it has 1 proton. Oxygen is number 8. It has 8 protons. So which one has more positive charges? Hydrogen or oxygen? If you said oxygen, then you're correct. It has 8 protons and therefore 8 positive charges. Now, what are negative charges, such as electrons, attracted to? They're attracted to positive charges. So if I'm an electron here and I like positive charges, who am I going to want to hang out with more? Oxygen or hydrogen? If you answered oxygen, then you're correct. Okay, so because oxygen has a lot more positive charges in the nucleus than these little hydrogens do, these electrons are going to pull towards oxygen. They want to hang out with him. And that is what we call electronegativity. Electronegativity is the ability of an atom to attract electrons. So here in this case, oxygen is very electronegative compared to hydrogen. He sucks up all of those electrons and drags it over there to him because, he's the cool kid to them. All right, so they hang out with him. So that means, for the most part, these electrons are going to hang out over here towards this end of the molecule more so than they do over here. Remember, these electrons, even though they're pictured this way, they are moving. They're not looking like this all the time. This is just a general idea of where they will be located at any given time on average. But again, this oxygen atom is pulling them over there, so they're hanging out with him more than he is with these hydrogen atoms. That's what electronegativity is. So in water, the oxygen atom is more electronegative and therefore is going to have all those negative charges hanging out beside him. So that's going to create an overall partial negative charge to this pole of that atom, and a partial positive charge will be over here towards the hydrogens. All right, and this represents that very well. You'll see this is a space filling model. So you have your oxygen atom in the center and you have your hydrogen atoms over here. So you have H2O, and you'll have this oxygen, which is partially negative. Again, because he's more electronegative. He's dragging in, sucking up all those electrons, making them hang out with him because he is more positively charged in the nucleus. That's why they want to come over and hang out with him rather than those puny little single proton hydrogens. Likewise, since all of these negative charges, the electrons are being dragged over here towards oxygen, that means less of them will be over here with hydrogen. So we'll have a partial positive charge over there. So overall, electronegativity creates uneven distribution of our electrons, making them have partial negative and partial positive poles. That's what we call it that's why we call it a polar bond, polar covalent. So what do you think will happen if this molecule comes in contact with another polar molecule? Let's just say for all intents and purposes that it's another water. So I'm going to draw it. Here's my oxygen. Here's my, this is terrible. I need to work on this some. Here's my hydrogens. I wish there's a way to back up. I know there's a way, I just haven't figured it out yet. Oh, no. Okay, let's just try again. So here I have an oxygen, and here I have my hydrogens. This is going to be partially positive, and here we have a partial negative. So if these two water molecules were placed next to each other, what do you think would happen? Would there be any attraction or repulsion going on? Just think about it for a second. All right, so the answer is that there would be some attraction and repulsion going on because, remember, opposites attract. And the same rules apply for partial positives and partial negatives. So if we look at this image here, it shows you lots of water molecules, right? Here's a water molecule, here's a water molecule, there's one, so on and so forth. All the reds are oxygens, all the whites are hydrogens. And you'll notice that you see these dotted lines. Those dotted lines are representative of our third type of bond, which is our hydrogen bonds. And hydrogen bonds are weak attractions between slightly positive hydrogens and a slightly negative atom. So here, for example, we have this shows you our oxygens and hydrogens and the partial positives and the partial negatives of this molecule of water. There's a partial positive here on this hydrogen. There's a partial negative on this oxygen. So that partial positive and partial negative is attracted to one another. And that attraction is a hydrogen bond. It's represented by these dotted lines. And so you can see those dotted lines in between every single hydrogen and oxygen of another atom. Now, for clarity, I want to make sure y'all understand this. In this molecule of water, H2O, this single molecule, this is a polar covalent bond between this oxygen and hydrogen. This is a polar covalent bond between this oxygen and hydrogen. The dotted lines that are between two separate water molecules that are showing the attraction between the partial positives and negatives between two separate molecules are the hydrogen bonds. All right. So next, let's talk about chemical formulas and reactions. We won't talk too much about this right now. I just wanted you to know some general definitions, reactants and products. So reactants are the things that participate in a reaction, and the products are what you get from that reaction. So here's an example of a chemical formula in a reaction. All right, so C6H12O6 plus oxygen will yield CO2, which is carbon dioxide, water, and ATP. The reactants are in red. These are the things that are participating in the reaction. The products are in blue. All right, so the reactants are the things that the arrow is pointing away from. Always notice where the arrow is going. The arrow will always point towards the products. Okay, so next, balancing equations. So this is more of a chemistry thing, so we won't spend a whole lot of time on it, but basically a balanced equation is where we have the same thing, the same atoms on both sides of the arrow. All right, so this is our general equation for photosynthesis. We'll get all into that in another chapter, but carbon dioxide plus water yields glucose and oxygen. If we were to break it down and count up how many carbons and how many oxygens and how many hydrogens are on this side of the arrow, we would get the same thing on the opposite side. So let's just count up the carbons. There's 6 carbons on this side of the equation. Well, what do you know? There's 6 carbons on that side of the equation. If we count up the oxygens, there's 1, 2, and now we got to multiply that times 6, right? Because there's 6 CO2, so we got to multiply this oxygen times 6, or O2 times 6. So that'd be a total of 6 times 2 is 12, plus, here's another one, but we got to do it 6 times because we see there's 6 water, so that's another 6. All right, so that's a total of 18. If we do the same on this on this side, we have 6 plus 12. Well, if you add that together, we get 18 again. So again, if you do that with hydrogen, you'll get the same thing. It is a balanced equation. There's the same number of every type of atom on one side of the equation as there is the other. All right, so next, the next topic in our book is water's importance. Water is obviously very important, right? Because life began in water. It is the most important molecule on Earth. Most of our living organisms are made up primarily of water. It has unique properties that make it very great for supporting life. And the properties that I'm referring to stem from the structure of the molecule. Here's a fun fact. Water has been found on Mars, as well as some moons of some planets, I believe, including, if I remember correctly, Saturn. So anyway, which is very interesting because, we previously thought, if we find, life on another planet, it must have to have water. And so it's interesting that we have now found water on other planets or moons of other planets. However, it's almost exclusively in ice. I would be interested as a scientist to get these samples and look at it under a microscope and see if there's anything in there. Maybe there is, maybe there's not. I don't know. Okay, so what are these properties of water that make it so conducive to living things? They are solvency, cohesion and adhesion, high surface tension, heat capacity, heat of vaporization, and varying density. Let's start with the first one, solvency. So water can act as a solvent. A solvent is a substance that is capable of dissolving something else. And particularly with water, it is capable of dissolving other polar compounds as well as ionic compounds, like salt, for example. Now, the things that we dissolve in a solvent is called the solute. Solutes are particles that we dissolve in a solvent. And together they make up a solution. So a solution equals the solutes plus the solvent. So, for example, let's say I'm going to make some Kool-Aid. The water would be the solvent. What would be the solute? A little flavoring packet. It has a bunch of particles in it that you pour into the water and dissolve it. And then the solution would be the result of me pouring the solute and mixing it into my water, the solvent. Okay. Next, another extension of solvency is that we said that water is a great solvent for ionic and polar compounds. If something dissolves in water, we call that substance hydrophilic. Break it down. What does hydrophilic mean? Hydrophilic. Hydro means water. Philic means it likes it. So a polar compound are hydrophilic. They like water. They mix well with water. Nonpolar compounds are hydrophobic. Remember, because nonpolar compounds are made up of nonpolar covalent bonds, which means they share electrons equally and do not have partial positives and partial negative charges to be attracted to a polar compound like water. So polar compounds are hydrophilic. They like water. They like other polar things. Nonpolar compounds are hydrophobic. They don't like water because nonpolar compounds don't mix with water. They don't like it. They don't have, all right, let me give you an example. Oil. If you take oil and water, put it in a cup, and you can shake it as hard as you want to, and then you set it on the table, eventually you're going to see separation. That oil and that water is going to separate because they don't like each other, because one's polar and one's nonpolar. The oil is nonpolar and the water is polar. They don't mix. So let's do another example. Oh, before I move on to the next example, this picture right here is a close-up of oil and water on a microscope slide. All right, so you can see the water here and the oil droplets, they stick together. They don't mix with the water. All right, next, how about sugar? Sugar, is it hydrophilic or hydrophobic? Sugar is hydrophilic. It mixes well with water. If you stick sugar inside of a bucket of water and stir it around, it will mix well with water. And why? Here's an example of a sugar. This is glucose. And you can see it shows all the different carbons in black. It has hydrogens in gray and oxygens in red. But it shows you all the different partial negatives and partial positives. These partial negatives and partial positives will be attracted to... Oh, this is so hard. It will be attracted to... Let me just start over again. Apparently, I just don't hold my pen correctly, like normal pens, because when I do it the way I normally write, it just doesn't. It's not happy with me. Okay, so here is an oxygen. Here is my hydrogens, and we said our hydrogens have a partial positive charge, and the oxygens have a partial negative charge. Well, there's going to be a hydrogen bond that forms here. There'll be a hydrogen bond that forms there. And there'll be another hydrogen bond that forms here that will be attached to, you know, the oxygen of another glucose molecule. I'm not going to take the time to draw all that because I suck at drawing, but hopefully you see what I mean. We have all these partial positives and partial negatives that will be attracted to the partial positives and negatives of water. Okay. So next, water is cohesive and adhesive. So these are just some straight definitions. I won't bore you to death with with reading everything to you, but basically cohesion, water attracts to other water molecules. Adhesion, water is attracted to other polar surfaces besides water. So you need to know that differentiation. Cohesion, water is attracted to water because they're both polar, right? And then adhesion, water is attracted to other polar things besides water. All right, so the last point on that slide was that, but for that reason, it contributes to water's ability to transport in plants as well as other living systems such as humans. So here we see, in this picture, of course, we have a human. If we look inside of the blood vessels, most of the stuff in blood, like if you were to go have your blood drawn, it's, you know, big old red tube. If you were to analyze the contents of it, it's mostly water, okay? And it is attracted to other water molecules as well as the lining of the blood vessels. All right, and it helps blood flow because of that. Same thing with water transport in the vessels of plants. So plants have vessels inside of them that is kind of similar to blood vessels. They're called phloem and xylem, that water will transport in as well. So when water is taken up by the roots of plants, it will travel all the way up to the top of that tree into the leaves and even escape as water vapor. And it's able to do that because of cohesion and adhesion, because the water molecules stick together and they also are attracted to the surfaces of the vessels, the lining of them. Okay, next, water has surface tension. So what that means, ooh, God, I'm so terrible at this, y'all. I swear I'm drawing a straight line and it still goes down. Surface tension. Okay, water has high surface tension. Water molecules at the surface of water cling more tightly to each other than to the air above. All right, so because of that, bugs or anything that's really lightweight, as you can see here, are able to sit on top of the water. So you can see this guy here, this little bug, like striders, for example, spiders, I've seen them, you know, crawling around literally on top of the water. They're able to literally walk on water because of surface tension. The surface tension of water is so high because they are clinging to one another due to cohesion, and they're not clinging to the air molecules. So these bugs or lightweight things can sit on top of water. And that's due to hydrogen bonding between water molecules. Next, high heat capacity and vaporization. So water has a high capacity for heat. What does that mean? If you were to take a look at these items here, water, methanol, ethanol, and ethyl acetate, and compare their boiling points, you will see that water has the highest boiling point. So that's because water has loads of hydrogen bonds throughout. And that allows water to absorb heat without changing temperature. That's why the temperature of water rises and falls slowly. Think about, you know, say you're cooking and you put a pot of water on the stove. It seems like it takes forever for that water to boil, right? That's because it absorbs a lot of energy without changing that temperature. Let me think of another example. It is, let's see, June, it's May. So it's May right now, May 2020. If I were to go jump in the pond outside my house right now, even though it's May and it's pretty doggone hot outside, that water is still going to be much colder than the air is. That's because it takes a lot of thermal energy, a lot of heat, in order to change water temperature comparative to how easy it is to change the temperature of the air. The temperature of the air is, changes from 12 p.m. to 2 p.m. temperature will rise or it'll fall, and can be pretty drastic. However, that's not the case with water because it has a high capacity for heat. It does not change temperature easily. It has to have lots of thermal energy in order to change temperature, which is a good thing. So the fact that the temperature of water rises and falls slowly and it requires so much thermal heat in order to, thermal energy in order to change it, that allows for organisms that are maintained of mostly water, like all the living things on Earth, to maintain homeostasis. Remember, we talked about that in chapter 1. Homeostasis was keeping an internal balance. If we were made up of mostly ethanol instead of water, well, first of all, that wouldn't even be possible because ethanol is alcohol. And if we were made up of mostly alcohol, well, we'd be drunk and we'd be dead. But anyway, let's say for all intents and purposes, hypothetically, our body temperature would be very sporadic compared to if our body was made up of mostly water, which it is. Next, heat of vaporization. It takes a great deal of energy to break those hydrogen bonds in order for water to evaporate. So in order for, when you boil a pot of water and you see all that steam coming off of it, what is it? It's water molecules. It's water vapor in the air. And they have gotten into the air because they broke free. They broke hydrogen bonds with the liquid water and then were aerosolized into the air. So we have a very high heat of vaporization, which is related to the heat capacity for water. Next. Water has varying density. Ice is less dense than water, and that's very unlike other substances. As water freezes, it actually expands and gets bigger. So if you've ever, of course, you've gotten a cup of ice before, right, and filled it with water, and then you notice the ice floated. It didn't sink. It actually became less dense as a solid. It's not as common as the other way around. So that's another thing that makes life possible. Is the varying density of water. It helps ice act as an insulator. This picture kind of shows you a graph of that. It shows density compared to temperature. So over here at really high temperatures, close to 100 degrees Celsius, which is boiling point, density is around, 0.95-ish. As we lower the temperature to around 4 degrees, think around the temperature of your refrigerator, you'll see that we have a density of around 1, very high. But as soon as the temperature reaches 0 degrees Celsius, which is the freezing point for water, our density drops down to 0.9, and therefore it will float in liquid water. Ice floats. Okay, that's water. Now, moving into 2.3, which is acids and bases. When we're defining whether a substance is an acid or a base, what we're actually talking about is how much hydrogen ions, H+, and how much hydroxide or hydroxyl ions they have, OH-. So I'm going to write that to the side. Hydroxyl, because sometimes texts will use these terms synonymously, hydroxide and hydroxyl ions. But think of it like a seesaw. So here we have our pH seesaw. You'll see how this relates to pH in a second. But again, when we're defining whether a substance is an acid or a base, we're talking about the relative concentrations of hydrogen and hydroxide ions. Which one is there more of? H+ or OH-? Now, water, when it dissociates, it does so in equal numbers of hydroxide and hydrogen and hydroxide ions. All right, so here we have water, H2O. When it dissociates, when it comes apart, it will break into a hydrogen ion and a hydroxide ion. So because of that, it's not an acid or a base. Because if we were to think about it on that seesaw, we would have just as many, here's my seesaw. Okay, good enough. Just as many hydroxide ions as I do hydrogen ions. All right, so the seesaw is neutral. Water is a neutral substance. It's not an acid and it's not a base, because there are just as many hydrogen ions as there are hydroxide ions. Now, an acidic solution has a high hydrogen concentration. So if we look at our seesaw, we have lots of hydrogen ions, relatively fewer hydroxide ions. Lemon juice, vinegar, coffee, those are all examples of acidic solutions. Hydrochloric acid, one of the most acidic solutions out there, is largely composed, your stomach acid is composed of lots of hydrochloric acid, hydrochloric acid, which is why it is so acidic in your stomach. It's like a pH of 1, which is very, very low, which is very acidic. If that breaks down, it breaks down into a hydrogen ion and a chloride ion. So lots of hydrogen ions relative to, well, no hydroxyl ions because it's a chloride. Oppositely, basic solutions have a low hydrogen concentration. Milk of magnesia, ammonia, bleach, those are all examples of basic solutions. But they either release hydroxide ions or they can take up hydrogen ions, making them fewer in solution. So overall, increasing hydroxide ion concentration or decreasing hydrogen ion concentration. So for example, sodium hydroxide. We have a sodium atom and a hydroxide ion. So in our little scale, our teeter-totter here, seesaw, we'll have relatively low numbers of hydrogen and high numbers of hydroxide as a basic solution. Just a FYI. Oof. Oh my goodness. Another name for a basic solution is an alkaline solution. You might see that in the text. Okay, so now that we know the difference between acids and bases and neutrality, let's talk about pH and the pH scale. So the pH is a mathematical way to indicate how much hydrogen ions are in a solution and therefore its acidity. And this is the mathematical equation. The pH is equal to the negative log of the hydrogen ion concentration. Don't freak out because I'm not going to ask you to calculate that for anything. I just want you to know. pH is the negative log of the hydrogen ion concentration. Now, the pH scale is a scale that ranges from 0 to 14, where 7 is neutral, and therefore there are just as many hydrogens as there are hydroxides, like water. If it's below 7, it is acidic, meaning more hydrogens than there are hydroxides. And oppositely, if it's basic, it will be above 7, and that will mean that there's more hydroxides than there is hydrogens. So let's look at this pH. This is our pH scale here. You can see it runs 0 to 14, 7's in the middle. So pure water, for example, we said it dissociates and forms just as many hydrogen ions as it does hydroxide ions and therefore is neutral. If we have high concentrations of hydrogen ions, it will yield a very low pH, which almost sounds kind of unintuitive, right? Because we said previously that lots of hydrogen ions means it's acidic. But it seems kind of backwards. Well, let me tell you why. Because our pH scale is the inverse of our pH calculation. We said to define pH mathematically, pH equals the negative log of the hydrogen ion concentration. So pH, because we have that negative sign, it's the inverse, right? So if we have lots of hydrogen ion concentrations, that means the pH is going to be very, very low. All right, so up here at 0, hydrochloric acid, which is very, 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 very acidic, like close to the pH of the stomach, which is 1, we have lots of hydrogen and it's very, very acidic. Oppositely down here, these are our basic solutions like sodium hydroxide, bleach, ammonia, oven cleaner, which is basically just ammonia. But anyway, we have increasing numbers of hydroxide ions relative to our numbers of hydrogen ions, and those are our basic solutions. Another thing you need to be aware of our pH scale is that it's a logarithmic scale. Okay, so we said the pH is the negative log of the hydrogen ion concentration. The logarithmic scale indicates that for every unit change, it represents a 10-fold increase or decrease. So between a pH of 8 and a pH of 9, that is a 10-fold change in the number of hydroxide / hydrogen ions. A pH of 4 here would be 10 times as acidic as a pH of 5. So we're going up in acidity going this way. A pH of 4 would be 10 times more acidic than a pH of 5. A pH of 10 is 100 times more basic than a pH of 8, which would be here. We get more basic as we go up or go down that way. Here's 8, here's 10. It's a 2 integer change, and that means that it's 100 times more basic because 10 times 10 is 100. All right, so how much more acidic is stomach acid than lemon juice? You should say 10 times more acidic. Good. All right, so how much more acidic is stomach acid compared to tomatoes? This is a 1, 2, 3 integer change. So you would calculate that by saying 10 times 10 times 10. And if you do the math, it is 1,000 times more acidic. Stomach acid is 1,000 times more acidic than a tomato. All right, next, buffers. So buffers are a chemical, or it can be a combination of chemicals that helps maintain pH. They can absorb excess hydrogen or hydroxide ions to help maintain homeostasis. That's really important for healthy living organisms like our own bodies. So, for example, it's very important for our blood to maintain its pH. Your blood should be approximately 7.4. Normal reference ranges for blood pH is between 7.35 and 7.45. Blood is, normally slightly basic. That's good. But if it falls below a pH of 7, that results in acidosis of the blood. If it falls if the pH rises above 7.8, then that is going to result in alkalosis. Remember, alkalosis or alkaline and basic is the same thing. So your blood's becoming too basic or too alkaline. Both of these are life-threatening conditions. So our body does have built-in mechanisms to help prevent that. For example, you can read in our textbook about the carbonic acid buffer. Our lungs, even the way we breathe, if we hypoventilate or hyperventilate, it can adjust our blood pH because of the varying amounts of carbon dioxide and oxygen that are coming in and out of the body, which basically there's a domino effect on a lot of other different chemical reactions that can take place that can alter our blood pH through just the way we're breathing. And we won't go all into that, but you'll talk about it if you have anatomy and physiology. At least you will if you have it with me. Anyway, even our kidneys have a mechanism to help encourage altering the pH of the blood when necessary. So lots of different mechanisms in the body are built in to prevent pH changes because these are life-threatening conditions. All right, so for example, acidosis. If your blood becomes too acidic, you will have effects on the central nervous system. It can cause you to lose consciousness. You can get confused, headaches, go into a coma. You'll have muscular weakness. You'll most likely have diarrhea with nausea and vomiting. Your heart can have arrhythmia and sporadic ways in which it beats. Your heart rate may go up, and you'll have some respiratory issues as well, coughing, shortness of breath, etc. All right, so that is pH, and that concludes chapter 2. So hopefully y'all enjoyed this. Hopefully I'm doing a little bit better as we progress with this Wacom device, and that y'all are enjoying these narrated lectures.